The last few lessons, we've been discussing solutions and how we prepare solutions. Many of the solutions we're going to make in this course are either chemicals called acids or chemicals called bases. Now, in the next couple of lessons, we're going to learn more in detail about what those things are. But for today, let us start by looking at a video of what they can do. All right, so here, what we've got here is, in this video, we've got two Coke cans. Now I'm going to turn on the volume and I'm just going to narrate it myself. We're going to have two Coke cans, which are made of aluminium, okay? Now, we're going to watch as acid gets added to one can and base gets added to the other can, okay? So we're just going to watch for a second here. Just going to play it, hoping this plays for you guys. Okay, so sodium hydroxide on the left is a base, and hydrochloric acid on the right is an acid, obviously. Now, we're looking for signs of things happening. Okay, so we can tell that a major change is occurring because we can see some fizzing. We can see evidence that change is occurring. So first of all, we can see fizzing, quite a lot of it. We see bubbling. We see steam being produced. All of these are signs that a chemical reaction is happening. We see that aluminium is starting to change its appearance. It's going from being a solid can to basically being eaten away. And what you see, the red stuff left over is just the plastic that's on the outside of the aluminium can. The metal itself is actually being corroded away. It's actually being eaten away. And we've seen evidence like this before in chemical reactions in junior cert, where we saw fizzing, we saw bubbling, we saw steam, all of that being produced tells us a chemical reaction is happening. Now, the reason why they haven't used Pepsi cans in this is because Pepsi cans are made of steel and they won't react with acid and alkalis. Okay, so look, pretty much nothing left over there. Okay, now that's all I really wanted to show you there. Okay, but just a note again, what aluminium? And what you've just seen there is aluminium reacting with the acids and alkalis and being destroyed basically. Now, Coke cans are not easy to destroy. Okay, you can see the Coke can that gets dumped 10 years ago. Someone drops it on the ground, squashes it with their foot and litters and leaves it there in the grass. That could still be there 15, 20 years later. It's not easy to destroy, yet these two chemicals that we just seen can do it really, really easily. So these two chemicals, what are they called again? They're called acids and bases, okay? So when mixed with an acid or base, we say that the aluminium gets corroded, which kind of means eaten away. It reacts and it's turned into something else. So if the aluminium gets corroded, then we could say that these chemicals are corrosive. What they do is they corrode other chemicals, corrosive. So just like they can corrode aluminium cans, they can corrode lots of other materials as well. So for example, human skin and human eyes. So the reason why we're introducing this idea is because for us to understand that acids and bases can be very dangerous because they're corrosive. Just like what they can do with the aluminium, they could do the same with your skin and eyes. Not all acids and alkalis can do this, but many of them can, especially if they're in high concentration. So acids and bases are often accompanied by this symbol. You'll find a symbol on the bottle or on the packet that you buy them in. And this symbol here means corrosive. I want you to look at it carefully and identify what you can see. I'm drawing your attention to this area here, where there is a test tube with some drops being poured onto human skin, onto a hand, and it's kind of eating away at the flesh. Again, we say the flesh is being corroded. Here it has been poured onto a surface, a metal surface top, a wooden surface top, and again, depending on the acid, it might also corrode the surface. Okay, so that's what this warning sign tells us. Is something that's very important to be aware of, because if you go on to work with chemicals, you go on to work in chemistry, you need to understand the risks that you're dealing with. Now, that doesn't mean we don't touch these or we have to be afraid of them. It just means that we have to be careful when we use them. So gloves will protect you against them. Goggles will protect you against them, and wearing a lab coat with long arms so that if you spill it, the lab coat protects your skin from it. You could take the lab coat off quickly and hopefully it hasn't gotten on your skin. But obviously, and also as well, you have to make yourself aware of how strong or how dangerous is the acid that you're dealing with. So that's the first thing to introduce. Acids and alkalis or acids and bases. Acids and bases are corrosive. Okay, so acids and bases are corrosive. That's the first thing to know. All right. So what we're going to do now is we are going to get you guys to pause the video and have a look at these three questions for me. So please do that now. Question 33 to 35. Pause the video, do that now, please. Okay, so for 33, hopefully we're talking about things that we saw fizzing, we saw bubbling, saw steam generated, and the aluminium changed its appearance. That's describe what you observe, means describe what you saw happening. So fizzing, bubbling, steam generated, and aluminium changed its shape or form. What do these observations tell you about what's happening? A chemical reaction is happening. Okay, so that's what you want to say there. Or you could say the aluminium is reacting with the acids or the alkalis. Chemical reaction is happening. That's what that tells us. And lastly, which hazard is associated with acids and bases? They are corrosive. So keyword here, you want to be saying that they are corrosive. All right, so that's acids and alkalis and the real safety concern with them. The next thing is, well, what are acids and alkalis, and what substances are acids and alkalis? Well, the easiest way to begin is by thinking about substances every day that we find that are acids. Okay. All right. So first of all, a very common example of an acid is the substance vinegar. So we'll all be familiar with vinegar. You take vinegar and you put it on your chips. Okay. Now, some people love vinegar. I don't particularly like it, but again, that's just down to people's preference. It kind of has a soury taste to it. So people who like sour taste tend to like vinegar. So if you dip your finger in it, put it in your mouth, you would find it's hard to describe the exact taste, but definitely, I think sour would be the word that most people would use to describe it. Another thing that would have acid in it is cola. Okay, now cola doesn't really taste sour. And the reason for this is because it's got so much sugar in it that it overpowers the sourness. But if you were to drink, for example, carbonated water, fizzy water, that can kind of, some people, I don't particularly like fizzy water either because I find that it has quite a sour taste. Okay, so if you again, just sparkling water is what I'm talking about. So cola is essentially sparkling water with loads of sugar and flavors added. So anything that's maybe we shouldn't say cola, maybe we should just say any carbonated drinks or sparkling drinks. Particularly when there's no sugar and flavor added, that's when you can notice that it has a little bit of a sour taste. Lemons, limes, oranges, citrus fruits, pineapple. Most of these are nice and sweet because they've got a lot of sugar, but definitely still sour, particularly lemons and limes. They don't have quite as much sugar in them, so you can still taste quite the sourness from them. Pineapple is another citrus fruit. It is also acidic, but it has a lot more sugar in it, so it tastes a bit sweeter. But citrus fruits, again, an example of a sour tasting substance that is acidic. All right, so these three things are stuff that we will be commonly associated with tasting, and we will find that they taste sour. Acidus is an old Latin word that literally means sour tasting. This is actually where the name came from, okay? So it was shortened to acid after. So acids were things that tasted sour. Now, obviously, if you wanted to test if something is sour, if you wanted to test if something was an acid, tasting it would not be a good way of doing that anymore because these ones are fine, but some of the ones are much more dangerous. So we don't really want to be tasting stuff. But back when things were being named thousands of years ago, this is literally what they had to do. They didn't have any other way of testing whether something is an acid or a base. We do now, but they didn't then. Okay, so I'm going to get rid of that now. So acidus means sour tasting. We get rid of that. These are acids, and these are what we call everyday acids or common acids. Maybe we call them common acids. Common acids. Common just means you can find them in your everyday items. So vinegar, cola, citrus fruits. Other things then include batteries. So batteries would not work. So what batteries. I don't know if you've ever seen them. The big, massive battery, and again, they don't. What was I going to say? Yeah, they don't work unless they're full of acid. So battery is another one that has acid in it. And the last thing is your stomach. Now, anybody who's ever been sick, who's vomited, maybe after you get a stomach bug or after you've been on a night out, you have too much to drink, you get sick. You will all know that the content of your stomach is very sour. You could taste it in your mouth when it comes back up. And again, the reason for that is it's actually full of acid, so stomach acid. These are common or everyday acids, and we need to know some of these. So in a second, we are going to make a list of these. Okay. Let's now think about, well, vinegar is really the name of a substance. It's not the name of an acid. So what acid is actually in here? So the name of the acid that's in vinegar is called ethanoic acid. Ethanoic acid. So vinegar is a solution of ethanoic acid and water, basically. So it's not pure ethanoic acid, it's ethanoic acid in water, certain concentration. Cola is carbonic acid, and any fizzy drink is carbonic acid. So it's carbon dioxide sprayed into water, okay, and this gives it its fizz and it turns it slightly acidic. Citrus fruits nicely have the name citric acid. Battery acid is sulfuric acid. And stomach acid is hydrochloric acid. Now, these are what we call our common acids, okay? And in a second, we're going to make a list of those, okay? So take a good look at those. All right, now in your notes copy, what I want you to do is I want you to pause. I actually want you to split a table down the middle here, and we're going to put common acids here on the right. Common acids, like that. And on the left, we're going to put lab acids. Now, we've just talked about 5 common acids. What I want you to do is make a note of as many of them as you can remember. Pause the video and do that now. Okay, so I want you to name the common substance that they're in, and then if you can, name the acid as well. Okay, so you should only be playing if you've had a good go at doing that. This is what you should have had. Common acids: vinegar, cola, citrus fruits, batteries, stomach acid. All right, so for our lab acids, these are acids where we actually pay more attention to the name of the acid, and are the common ones that we use in the lab, and we're going to be using this here. Okay, our 3 most common acids are hydrochloric acid, which is the same as the one in your stomach, but we use it at higher concentrations than it would be in your stomach. Hydrochloric acid is the first one, and the chemical formula for this is HCl, hydrogen and a chlorine. 1 hydrogen atom, 1 chlorine atom. Hydrochloric acid. The second one then is what we call nitric acid. I'm hoping you're seeing a theme here in that they all end in ic, IC. So anything in ic, look, sulfuric, nitric, hydrochloric, citric. Again, that's a good sign that we're talking about an acid. Nitric acid, again, has nitrogen in it. It's HNO3. And then the last one that we're going to talk about is sulfuric acid, that same one that's in batteries, sulfuric acid. And the chemical formula for this is H2SO4. Okay, so these are our 3 most common lab acids. There are other ones, but these are the ones we use most often. So what I want you to do is take a good look at those, study them, study the formulas. And what we're going to do now is we're going to add them to our list, lab acids. Pause the video, do that now, please. Okay, so checking this. Good, what I want you to do now is I want you to pull away your notes, where you have to take those down, open your practice copy, and we're going to answer questions 36 and 37 for me. Please do that now. And now you can use this to check that you got those right, please. Pause the video and do that now. All right, so we've just learned about what acids can do. They are corrosive. We've learned about some different common acids where we come across them in our everyday lives, and then some lab acids, the names of the important ones that we're going to be using quite often. What we want to now discuss is what makes these things acids. Why are they sour tasting? Why are they corrosive? And why are they called acids at all in the first place? Okay, now for junior cycle, you probably would have learned things like, oh, acids are substances that have pH of less than 7. Neutral substances are substances with a pH of exactly 7, and bases or alkalis, you might have learned that the bases and alkalis are interchangeable, that word. That those are substances with pHs of greater than 7. Now, all of those things are true, but they don't really describe or help us to understand what is an acid and what is a base. It doesn't really help us to understand what those really are. So today we're going to focus on an acid. What makes acids acid? Okay, right. Let's say, for example, we have the substance hydrogen chloride, HCl. Okay, we have this substance. Hydrogen chloride is a gas, okay? And we've learned before that hydrogen chloride would be made up of, sorry, I wanted a red marker there. Hydrogen chloride is a gas that's made up of hydrogen, a H plus ion, combined with a Cl minus ion like this. So it's an ionic substance, okay? Oh, it's pretty ionic in character. It's made of a hydrogen ion and a chlorine ion combined together. All right. Now, this substance is a gas. Now, it turns out that if you take this gas, hydrogen chloride, and you bubble it through some water. So here I've got a beaker, and it contains H2O. So I've got water. I'm going to add my water to my beaker. And what I'm going to do is I'm going to take my hydrogen chloride, and I'm going to bubble it through some water so that it dissolves. I'm going to dissolve hydrogen chloride in the water. What we find is that when the hydrogen chloride dissolves, the ions which make up the compound, the hydrogen and chlorine, get pulled apart. They get separated from each other so that they look like this. H plus and a Cl minus. Now, obviously, in real life, if we were doing this, there would be many more than just these two ions, but each hydrogen chloride would be pulled apart so that it's separated. We say that the ions dissociate from each other. I think there's two S's here. Dissociate. Which kind of means, I think this is like short for disassociate. So associated, if you're associated with someone, it means you're together with them. So associated means they're together. So this kind of is like they're associated here, together, and they're dissociated down here. They're separated from each other. So dissociate means separate, basically. So when we mix them with water, when they dissolve in water, they dissociate from each other. Now, when the ions dissociate, we can kind of write an equation for this. So obviously we started with hydrogen chloride, HCl. And when they dissociated, they split up to give us H plus, which is AQ, which means aqueous, which means they're dissolved now, plus a Cl minus, which is also aqueous. It's also dissolved. Okay, so this here is what we would call an equation to just describe what's happening. HCl is splitting to give us H plus Cl minus. This is like dissociation happening. So when this happens, the water now contains a lot more of these separate H plus ions. Okay, so we call this a H plus ion. When acids dissociate in water, we put a lot of extra H plus ions into the water. This here is what makes a substance acidic. If water has a lot of H plus ions dissolved in it, this makes the solution acidic. Now, and a scientist called Arrhenius, or Irenaeus, I'm not sure exactly what the Greeks would call him, but Irenaeus, funny word, Irenaeus, okay, he was the first guy to kind of figure out that this is what was happening. So he was the first person to explain how this works. And according to Irenaeus, then, an acid is, so this was what an acid was. An acid was a substance which dissociated in water to produce H plus ions. So something like HCl dissociated in water, separated to produce H plus ions. Now also produce Cl minus ions, but this doesn't affect whether something's acidic or not. It's how many H plus ions are present that affects whether something is acidic. So according to Irenaeus, okay, his definition of an acid was it's a substance which dissociates in water, produce H plus ions. So at this stage, what we're going to do is we are going to get you guys to take that down. So this is a definition of an acid. Now, unfortunately, it's not the only definition we're going to talk about because it's not a perfect definition. There are some problems with it, which means that it's changed over time. So you have to remember this definition, and if you have to remember that this was Arrhenius's definition, because there's other people we're going to talk about too. So according to Arrhenius, so when you're writing this down, you're going to write Arrhenius's definition of an acid. An acid is a substance that dissociated in water to produce H plus ions. So please pause the video and write that down now. Now, we're going to take a look in a little bit more detail. I'm going to stick with Arrhenius for a second, okay? Now, according to Arrhenius, we could have two different scenarios where we have two different acids and we're dissociating them both in water. So we're going to call it acid A. I'm going to call this acid B. Okay. Okay. And we're going to say that acid A looks like this and acid B looks like this. Okay, so these are the molecules. Now, of course, this is then before they dissociate in water. We know that both of these substances are going to dissociate to produce H plus ions. Okay, both of these acids are going to do that because that's what an acid does. But according to Arrhenius, not all acids act exactly the same. So for example, when we put A into water, this substance might only produce, so say if we had the same amount of each one, same quantity, say if we had 1 mole of this and we had 1 mole of this, so the same quantity of both of the acids. Acid A, when it's added to water, might only some of the molecules dissociate. So let's say a couple of them dissociate so that we produce 2 H plus ions and the rest stay as the full molecule, A, 2, 3, 4, 5. So most of the acid molecules stay together. They do not dissociate, but a few of them do dissociate to produce H plus ions. So that's acid A. Acid B is a lot more likely to split up and produce H plus ions, so that only one of the molecules stays intact as B, and all of the rest of them split up to produce H plus ions. Sorry, I'll go with the purple one again. So by starting with the same amount of each acid, or the same quantity, same number of moles of each acid, we can end up with acids that produce a different number of H plus ions. Okay, now, what we would say then about these two acids is that they're not equal. The one on the left, A, is less acidic because it does not fully dissociate. Only some of the molecules dissociate to produce H plus ions. So this is less acidic. Whereas acid B on the right here is much more acidic because nearly all of the molecules this time are dissociated to produce H plus ions. There's nearly none of the original acid left, B. Okay, so this is how acids can be different from each other. Now, for example, this is why we can maybe drink things like vinegar, or we can drink things like, we can eat things like citrus fruits, because they're not highly, or they're not really strongly acidic, like acid A here. Whereas battery acid, for example, the acid you find in batteries, you definitely cannot drink this. In fact, you can't put this anywhere near your skin. It will burn you very badly. Okay, so that would be more acidic, like B. So according to Arrhenius, these are the two different kinds of acids, if you like. Okay, now what he termed these is he termed these weak acids, and he termed these ones B, strong acids. So how did he define them? He said weak acids are acids which dissociate only slightly in water. So they produce fewer H plus ions, whereas strong acids are acids which dissociate fully in water. They produce more hydrogen ions, or H plus ions. All right, so what we are going to do at this stage is I'm going to get you guys to have a look at this now and writing down here these two definitions in red. Here. Okay, and lastly, I want to point out why is it to do with these hydrogen ions? Why are these always the ones that are interesting? Well, if you go back to our formulas for the acids, look up here for a second, you'll notice that they all have hydrogen in them. So hydrochloric acid has HCl, nitric acid has HNO3, sulfuric acid has two H's, H2SO4, which means all of these molecules can allow a hydrogen atom to drop off, because this here is a H to a Cl. The H can fall off. This here is a H to an N to three O's. Again, the hydrogen can drop off. So you see what I mean? That's where the hydrogens are coming from. Acids always have hydrogen in them, and when they drop off, they're hydrogen ions. So I just felt like, okay, sorry, I'm after losing my place here now. Yeah. Okay, so that there is, according to Arrhenius, what is a strong and weak acid. So I want to make sure you have those down now. Pause the video and write. Okay, now that's not the end of the story when it comes to acids. There's a more updated definition of acids. So Arrhenius was one of the first guys, and it's very important that we remember what he said. But his definition or his theory of acids wasn't perfect. I'll give you a couple of reasons why. One of the reasons was, when you look at his definition, he always talks about a substance that dissociates in water to produce H+ ions. One problem with this is that things can be acidic even when they don't involve water. So they're not always dissolved in water. So this provided a problem to his definition. So straight away, people started to discover that actually things can be acidic without involving water. They don't always need to be dissolved in water. They can act like acids without water. So they needed to change the definition. Another thing that people found out, and this is quite complicated, it's a little bit more complicated than how I'm going to explain it. I'm going to explain it nice and easily, is that the other part of his definition is that an acid is a substance that dissociates in water to produce H+ ions. This makes it sound like the H+ ions are floating around on their own in water like this. Now, scientists later discovered that this isn't actually what happens. What happens is that those hydrogen ions do this. So they stick to water molecules. So where this is O with two H's, this is a water molecule. Water, as we know from when we did the shapes of molecules, has two lone pairs like this. And what happens is the H+ ion that's produced by an acid, where are we? Yeah, the H+ is attracted to one of those lone pairs, like that. It's attracted to that lone pair, like this, so that it sticks to the lone pair. And what you get then is something that looks like this. Now, you might not have heard of this thing before because it's not a very common thing people talk about, but it's actually an O with three hydrogens. And it still has one lone pair, but it also has this extra plus charge from the ion, from the H+ ion. So what you have now is this thing H3O+. Okay, so this is H2O, water molecule, but this here is the H3O+ ion. So it's positively charged, and it's made of a water molecule with the hydrogen from an acid attached to it. This here is called the hydronium ion. Hydronium ion. Complicated idea, and it's not something you get asked that much about on the Lehman-Sutton course, but hopefully you can see the problem then with Arrhenius's definition, in that it doesn't always involve water, so that's step one, and it doesn't really involve free H+ ions floating around in the water, because as soon as they're made, what they do is they stick to water molecules like this to make hydronium ions. So the whole definition really is not right. So it's not like you have free H+ ions floating around in the water. Instead, you make hydronium ions. So straight away, it was a great effort from Arrhenius to explain what was going on, but it was just the reality was a little bit more complicated than he made out. So they have been updated. Okay, what have they been updated to? They've now been updated to talk more about actually the substance that loosen the H+ ion. So say, for example, we go back to chlorine and hydrogen again. So like this, HCl. Okay, now we've got to focus a little bit more on what the H is. If we think about the hydrogen atom, we know that hydrogen is an atom that has one electron. Now, when it combines with when it combines to form HCl, like this, we really have a H plus ion and a Cl minus ion, which means that the chlorine has taken the one electron away from the hydrogen. So this should not be brand new to us. We've done this before in bonding. So the chlorine has removed the electron from the hydrogen. So what else is in the hydrogen? Well, if you go to the periodic table, what you'll see is that hydrogen has an atomic number 1 and a mass number 1. What this means is that hydrogen has 1 proton and 0 neutrons. Now, atom of hydrogen also has 1 electron. But what we're saying in this case is when it's in an acid like this, hydrochloric acid, that electron is not there anymore because it's been transferred to the chlorine. So all that's left is just a proton because there's no neutron present. So this here is essentially the exact same as just a bare proton. So that's what a hydrogen ion kind of represents. A H plus ion is just a proton. And you will often hear these words used interchangeably. H plus ion is equal to a proton. All right. So this is, we learned before that chemistry is mostly about the way electrons move around. So electrons go from one atom to another atom. We said that protons don't really move around. They stay in the nucleus of atoms. They don't go anywhere else. But this is the way protons can move. Protons can move as a hydrogen ion. Okay. So if you've got hydrogen ions moving around, then you've essentially got protons being moved from one place to another. Because there's nothing else there. It's just a proton. Okay. So the newer definitions have been updated to include that idea, And the people who came up with it actually was 2 people. Their names were Branstad and Lowry. So they make up what we call the Branstad-Lowry theory of acids and bases. Branstad-Lowry. So these are the 2 people you need to think about. Arrhenius was the first guy, and Branstad-Lowry are the second. They're the second people. So what they said then is that an acid like this, HCl, is what we call a proton donor. It's something that can donate, give away a proton. So this here is acid together is an acid. And what it can do is it can give away the proton and leave behind just the Cl minus. So that's what an acid is. It's a proton donor. Proton donor. So that's what an acid is. Now, how do they account for then strong and weak acids? We know Arrhenius said, okay, so where are we? Sorry, we know Arrhenius said that a weak acid is one that does not fully dissociate, like this here. It only produces a few H plus ions. And they said that a strong acid was one that fully dissociates, produces a lot of H plus ions. Well, if we treat each of these hydrogen ions like a proton, instead of we swap the word hydrogen ion for proton, well, then what we can say is that a weak acid is a poor proton donor. Okay, it donates some protons, but only a few. So it's poor. Whereas a strong acid is one that donates a lot of protons. So this is a good proton donor. That there was Branstad-Lowry's updated definitions. Okay, so what we're going to do now is we are going to look at the writing in red, and we're going to make a note of this stuff here. Okay, so for 1 second, yeah. All right, so this is Branstad-Lowry theory. Again, make sure that you highlight the names properly so you don't mix them up. Branstad-Lowry's theory was that an acid is a proton donor, and weak acids are poor proton donors, while strong acids are good proton donors. So I wanted the big picture in your head. These diagrams really are the big picture, help you understand, okay, both. This first one shows that you have a substance, the molecule splitting into 2, and a H plus is now free in the water. Some acids produce a lot of H pluses, some acids produce only a few H pluses. We need to know the difference between them. We call them strong and weak, okay. The original definitions were Arrhenius, where he talked about that dissociation producing H pluses, but this is not always a good idea because this is not that accurate because not all acids need water, and we actually really produce a hydronium ion, not the H plus ions. Instead, we donate a proton which sticks to other things like water. Okay, so this is Branstad-Lowry's theory about proton donors, poor and good proton donors. Okay, all right, so quick summary there. So what we are looking at now is these questions should help to build our way through our understanding. So I think that that's it. We're actually going down 43. Okay, so these numbers are slightly different. I have, yeah. Okay, so we're going from 38. Actually, I'll zoom in here and we'll do them in steps. So we're going to do 38 to 44. Pause the video and do that now, please. From memory, don't be looking at your stuff. So close up your stuff, doing this from memory, please. Okay, so from 38 to 44, pause the video, do that now. Okay, and at this stage, I want you to go back and correct those from your notes. Okay, and then what we're doing is we're doing 45 down to 49. So pause the video and do that now, please. All right, guys, that I think. All right, no, we're gonna do another little bit here now. Just give me 1 second. Okay, so remember that acids, depending on how you think about it, they either are substances that produce H plus ions in water or they're substances that donate protons. It doesn't really matter how you think about that for now, but what I do want you to think about is that some molecules, for example, HCl, if we think about HCl, this molecule, or if we think about HNO3, when we think about these things, if you look at the whole molecule, if each of these is a molecule, then each molecule is able to donate only one proton. There is that one hydrogen ion or one proton that this is actually able to donate. So one proton. Once that molecule loses that one proton, that's it. It doesn't have any other ones to give away. Okay. So another word for one is mono. So these are what we call mono basic acids. So they have a base of one hydrogen ion. That's what they're based on. So they're acids based on the fact they have one hydrogen ion, mono basic acids. All right, so that's the first idea, that these molecules only have one proton or one hydrogen ion to actually give away. However, not all acids are like this. For example, if we look at this molecule H2SO4, H2SO4, what this looks like is it looks like this. Here's your SO4 ion, it's a complex ion, and here is your first hydrogen, and here's your second hydrogen. Remember, it's H2SO4. But if we take that substance and we dissolve it in some water, so put it in the water, what we can produce is this SO4 2 minus ion, like this, is free. And now you've produced two separate H plus ions. So for each one molecule, you can produce two protons or two hydrogen ions. So this is very different from the first acid, because those acids can only have one hydrogen per molecule, whereas this one has two hydrogen atoms per molecule. Okay, so two hydrogen ions per molecule, and we call this a di for two. This is a dibasic acid. All right, so what I want you to do is I want you to make a note now in your copy underneath where you've taken down about acids, about what monobasic and what dibasic acids are. So pause the video and write that down now. What you should have said is monobasic acids are acids which can donate one proton. Dibasic acids are acids which can donate two protons. And in fact, there's such thing as tribasic acids as well. So there are tribasic acids that work the same way. Tribasic means three protons. And one example we might come across in this course is H3PO4. So this here is a tri-basic acid, which works just like this dibasic acid, can release 3 protons for every 1 molecule. Okay, all right, so what we're going to do is I'm going to get you guys to pause the video, and I'm going to get you guys to have a go at questions 50 to 53. Pause the video, do that now from memory. Okay, and guys, that is it. Okay, just pointing out, actually, don't forget that distinguish, this word means tell the difference between. So describe mono and then describe di. So distinguish means give differences. Give differences. A good word that you can do here, that you can use to link these two things together, is whereas. So you could say monobasic acids are da 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 da, whereas dibasic acids are da 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 da. Okay, so whereas is a good word for linking together when we have a question like distinguish. So have another look at 53 now, and if you're not happy with what you've done there in terms of giving the difference between, and you've described both and linked them together with a link word like whereas, have another go at it now and make sure it's as good a quality as it should be. All right, so what I'm going to do is I'm going to finish it up there. In the next video, we're going to look at how acids react. And then in the video after that, we're going to look at what alkalis or bases are and how they react. Okay, all right, guys, that's it. I shall see you in the next video.